There is a specific kind of silence that exists only in the minds of theoretical physicists. It is not the silence of an empty room, or the quiet of a library, or the vacuum of space itself. It is the silence that falls over a conference hall when a slide is projected onto a screen, and every single person in the room realizes that the foundation of their life's work has just developed a crack. It is the silence of paradigm shift. It is the silence of fear. For decades, we have built a cathedral of understanding around the universe. We call it the Standard Model of Cosmology, often referred to as Lambda CDM. It is a beautiful structure. It is mathematically elegant. It predicts the motion of galaxies, the distribution of cosmic microwave background radiation, and the abundance of light elements with startling precision. It tells us how the universe began, how it evolved, and how it will end. We trusted it. We built our telescopes based on its predictions. We launched satellites into orbit expecting to see what the model told us we would see. But recently, the telescope looked anyway, and it found something that should not be there. Imagine a galaxy. Not a small dwarf galaxy scattered with a few million stars, struggling to hold itself together against the tidal forces of its neighbors. Imagine a galaxy with the mass of 100 billion stars. Imagine a structure fully formed, shining brightly, churning out heavy elements, hosting complex stellar populations. Now, place this galaxy in time. Do not place it here, in the present day, where such objects are common. Do not place it 5 billion years ago, when the universe was mature. Place it just 290 million years after the Big Bang. In the cosmological timeline, this is the blink of an eye. It is the cosmic infant stage. According to every simulation, every calculation, and every physical model we possess, there should not have been enough time for gravity to pull that much matter together. There should not have been enough time for the gas to cool, collapse, and ignite into stars. There should not have been enough time for those stars to die and seed the universe with the metals required to form the dust that obscures the light we are seeing. Every model said that was impossible. The physics of structure formation dictates a hierarchical process. Small things form first. They merge, they grow, they become big things over billions of years. To find a massive galaxy this early is like finding a fully grown oak tree sprouting from the soil one day, after the acorn was planted. It violates the rules of growth. It violates the rules of time. The telescope looked anyway. It was the James Webb Space Telescope, the most complex scientific instrument ever constructed by human hands. It was designed to see the first light. It was designed to push the boundary of the observable universe back to the edge of the Dark Ages. But even its engineers did not expect it to find this. It found one. Then it found another. Then it found hundreds more. These are not glitches. These are not errors in data processing. These are distinct, bright, massive objects sitting in the early universe, laughing at our equations. This discovery has sent a shockwave through the astrophysics community. It is not just a surprise, it is a crisis. When scientists say they are afraid, they do not mean they are scared of a monster. They are afraid that the map they are using to navigate reality is wrong. They are afraid that the dark matter we have postulated to hold these galaxies together might not behave the way we think. They are afraid that the gravity we understand might be incomplete. They are afraid that the timeline of the universe needs to be rewritten. And if the timeline is wrong, what else is wrong? What else have we missed? This video is not just about a galaxy. It is about the fragility of human knowledge. It is about the moment when observation collides with theory and theory loses. We are going to take a journey back to the beginning of time. We are going to walk through the physics of the early universe, step by step, to understand exactly why this discovery is so devastating to the current model. We are going to look at the telescope that saw it, the light that traveled across 13 billion years to reach us, and the data that keeps cosmologists awake at night. We will explore the implications. If these galaxies exist, then the universe is either older than we think, or it works in ways we do not understand. There are theories emerging to explain this. Some suggest early black holes that grew too fast. Some suggest dark matter that interacts differently than we assumed. Some suggest a complete overhaul of cosmology. But before we can solve the mystery, we must understand the crime scene. We must understand the universe we thought we knew, and then we must watch it break. The stakes could not be higher. We are looking at the possibility that the standard model of cosmology is incomplete. We are looking at the edge of known physics. And what we found there was not what we expected. We found what we were afraid of. Chapter 1: The Impossible Object. To understand the magnitude of this discovery, we must first isolate the object itself. We need to strip away the hype and look at the raw data. The galaxy in question, often identified in recent literature associated with the JADES survey, stands as a statistical outlier of such extreme proportions that it demands scrutiny. Let us define the parameters. We are talking about a redshift value that places this object at a time merely 290 million years post-Big Bang. In cosmological terms, redshift is the measure of how much the universe has expanded since the light left the object. A high redshift means the light has been traveling for almost the entire age of the universe. We are looking at a redshift of roughly 14 or higher. At this epoch, the universe was less than 2% of its current age. It was a hot, dense, chaotic place. The cosmic microwave background had cooled enough for atoms to form, but the first stars were just beginning to flicker on. The environment was hostile. Radiation was intense. The density of matter was higher, but it was also more uniform. Clumping matter together requires time. Gravity is a weak force. It is patient. It works over eons. To assemble a mass equivalent to 100 billion suns requires the accumulation of gas, the collapse of clouds, and the ignition of fusion. Consider the mass estimate: 100 billion stars. For context, the Milky Way galaxy, our home, contains somewhere between 100 billion and 400 billion stars. It took the Milky Way 13 billion years to reach this state. It merged with smaller galaxies. It consumed gas from the intergalactic medium. It grew slowly. To find a galaxy with similar mass at redshift 14 implies a formation rate that is physically prohibitive under standard models. How do we know the mass? We know it through the light. The telescope captures the photons. We analyze the spectrum. The brightness of the galaxy tells us how many stars are shining. But brightness can be deceptive. A galaxy could be bright because it has many stars, or because it has a few very massive, very bright stars. or because it has an active black hole at its center. This is where the spectroscopy becomes critical. The James Webb Space Telescope does not just take pictures, it takes fingerprints of light. It splits the light into its constituent colors. By analyzing the spectral lines, scientists can determine the composition of the object. They can see the signatures of hydrogen, oxygen, carbon. These are metals in astronomical terms. Elements heavier than helium are forged in the hearts of stars. They are released when stars die. If we see these elements in a galaxy that exists only 290 million years after the beginning, it means generations of stars have already lived and died. Think about the life cycle of a star. The first stars, population 3 stars, were massive and short-lived. They burned hot and fast. They might have lived for only a few million years before exploding as supernovae. Even if we assume the most efficient star formation possible, with stars forming immediately after the Dark Ages ended, the timeline is tight. To enrich the gas with enough metals to produce the spectrum we observe requires multiple generations of stellar evolution. It requires the supernova to explode, the shock waves to compress new gas clouds, and new stars to form from that enriched material. Doing this enough times to build a mass of 100 billion stars in less than 300 million years is akin to building a skyscraper by hand in the time it takes to lay the foundation. The efficiency required is off the charts. It violates the Eddington limit, the physical limit on how fast an object can accrete matter before the radiation pressure pushes the matter away. If a galaxy forms stars too fast, the light from those stars pushes the gas out, stopping further formation. These early galaxies should have self-regulated. They should have stalled. Instead, they appear to be roaring engines of creation. Furthermore, the structural integrity of such an object is questionable. In the early universe, dark matter halos were smaller. Galaxies form inside these halos. The gravity of the dark matter holds the gas in place so it can cool and form stars. If the galaxy is this massive, the dark matter halo must be equally massive. But simulations of the early universe do not predict dark matter halos of this size existing this early. The power spectrum of the initial fluctuations in the universe, measured by the Planck satellite, tells us how much clumping there was at the beginning. There were small fluctuations and large fluctuations. The large fluctuations were rare. The Tiohati, small ones were common. Structure grows from the small ones up. To have a halo massive enough to host a 100 billion star galaxy at redshift 14 requires a fluctuation that is statistically improbable. It is a sigma 5 event. It is an outlier that should not exist in the sample size of the observable universe. Yet Webb found not one, but hundreds. This suggests it is not a statistical fluke. It suggests the initial conditions were different. It suggests the power spectrum was different. It suggests that the universe started with more large-scale clumping than we thought. Let us delve deeper into the luminosity. The object is not just massive, it is bright. In fact, it is surprisingly bright for its age. This brightness poses a problem for dust. In local galaxies, dust absorbs light. In the early universe, we did not expect much dust because dust is made of metals, and metals come from stars. If there hasn't been enough time for stars to make metals, there shouldn't be dust. If there is no dust, the light should be blue and unobscured. However, some of these early galaxies show signs of reddening. This implies dust. If there is dust, there are metals. If there are metals, there have been many stars. This creates a circular constraint that tightens the noose around the standard model. The presence of dust implies a mature stellar population. A mature stellar population implies time. But we do not have the time. The redshift tells us the time. The redshift is determined by the expansion of the universe, which is well measured. We know how fast the universe is expanding. We know the distance. The time calculation is robust. So the error must be in the formation physics. There is another possibility that scientists are terrified to consider. What if the redshift is wrong? What if the galaxy is not actually that far away? What if it is a lower redshift object that is mimicking a high redshift signature? This is called interloper contamination. A nearby galaxy with specific properties could look like a distant galaxy in certain filters. This is why spectroscopy is vital. Photometry, measuring brightness in different filters, can give a hint of redshift, but spectroscopy confirms it. The James Webb Space Telescope has confirmed the redshifts of several of these candidates using NIR-SPEC, the near-infrared spectrograph. It sees the Lyman break. This is a drop-off in light caused by neutral hydrogen absorbing ultraviolet radiation. As the universe expands, this break moves into the infrared. Webb sees the break exactly where it should be for a redshift of 14. The confirmation is solid. These objects are real. They are distant. They are ancient. And they are impossible. The implications for the mass-to-light ratio are staggering. If the galaxy is this bright and it is this far away, it must be massive. Unless the stars are different? Could the first stars be fundamentally different from the stars we see today? Population 3 stars are theorized to be massive, perhaps hundreds of times the mass of the Sun. They would be incredibly bright. If this galaxy is composed entirely of supermassive population 3 stars, it could be brighter with less mass. But even then, the total mass required to hold the galaxy together gravitationally remains an issue. The stars need a potential well to sit in. They need dark matter. If the stars are supermassive, they live very short lives. They would have died out by the time we are observing them. We would be seeing the second generation. But the second generation should be less massive, dimmer. The light we see suggests ongoing, vigorous star formation. It suggests a system that is stable enough to sustain this output. Stability requires mass. Mass requires time to accumulate. We are back to the same wall. The time is insufficient. Consider the environment surrounding this galaxy. In the standard model, early galaxies are isolated. They are few and far between. The universe is mostly empty voids with small pockets of matter. To find a galaxy of this size implies a dense environment. It implies that this region of space was a hub of activity. If there is one, there should be others nearby. Clustering. Webb has indeed found that these galaxies are clustered. They are not alone. They are part of a protocluster. This increases the problem. Now, we are not talking about one impossible object. We are talking about a region of the universe that evolved too fast. A whole neighborhood of galaxies that defies the timeline. This suggests that the conditions in this part of the universe were unique, or that the conditions everywhere were different. if it is unique, we are incredibly lucky to be looking at the one spot where physics broke. If it is everywhere, then our model of the whole universe is broken. Given that Webb is finding more of these, as it looks deeper, the likelihood shifts toward the latter. The model is broken. We must also consider the role of black holes. Every massive galaxy today has a supermassive black hole at its center. The mass of the black hole correlates with the mass of the galaxy. In the early universe, we have found quasars. Quasars are active black holes feeding on gas. We have found quasars at high redshifts. They are also a problem. How did black holes grow so big so fast? They face the same Eddington limit problem. They cannot eat too fast or they blow the food away. Some theories suggest direct collapse black holes. Huge clouds of gas collapsing directly into a black hole without forming stars first. This could seed a massive black hole quickly. If this galaxy hosts a direct collapse black hole, it could explain the brightness. The light might not be from stars, but from the accretion disk of the black hole. However, the spectral lines show signs of stellar populations. It is not just a quasar, it is a galaxy. It is a hybrid monster, a massive stellar population, and potentially a massive black hole, both existing when the universe was a toddler. The coordination required for both to grow simultaneously is unheard of. It suggests a feedback mechanism we do not understand. The black hole should be heating the gas and stopping star formation. The stars should be blowing winds and stopping the black hole from feeding. Instead, they seem to be growing together. This chapter of our investigation focuses on the object itself because the object is the evidence. It is the smoking gun. In a court of law, if you find a fingerprint that does not match the suspect, you must reconsider the suspect. In science, if you find data that does not match the model, you must reconsider the model. The object is real. The data is verified. The model is lambda CDM. The mismatch is undeniable. We are not dealing with instrument error. We are not dealing with analysis bias. Multiple teams have analyzed this data. Multiple instruments have confirmed it. The impossible object sits in the sky, radiating photons that tell a story we cannot yet read. It tells a story of efficiency, of speed, of gravity acting with a vigor we have never witnessed. It challenges the notion of hierarchical structure formation. It challenges the nature of dark matter. It challenges the initial conditions of the Big Bang. As we move forward, we must keep this object in mind. It is the anchor of this mystery. Everything we discuss from here must explain how this object came to be. If our explanation cannot account for a 100 billion star galaxy at 290 million years, then our explanation is wrong. And right now, none of our explanations are good enough. Chapter 2: The Architecture of Time. To fully grasp why this discovery is so unsettling, we must reconstruct the timeline of the universe as we currently understand it. We need to walk through the epochs. We need to feel the passage of cosmic time. Only then can we appreciate the sheer impossibility of compressing galactic evolution into such a narrow window. The story begins at the singularity, or rather, just after it. We do not speak of the moment of the Big Bang itself as physics breaks down there. We speak of the Planck epoch, the earliest period of time. Then inflation. The universe expands exponentially. It smooths out. It flattens. Quantum fluctuations are stretched to macroscopic scales. These fluctuations are the seeds. They are the tiny variations in density that will eventually become galaxies. When inflation stops, the universe is a hot soup of particles. Quarks, gluons, electrons, photons. It is too hot for atoms to form. This is the radiation-dominated era. Light and matter are coupled. Photons bounce off electrons constantly. The universe is opaque. It is a fog of plasma. As the universe expands, it cools. This is the critical factor. Temperature drops as volume increases. Around 3 minutes after the Big Bang, nucleosynthesis occurs. Protons and neutrons fuse to form the nuclei of light elements: hydrogen, helium, a trace of lithium. This is Big Bang nucleosynthesis. The predictions for the abundance of these elements match our observations perfectly. This is one of the pillars of the Standard Model. It tells us the physics of the first few minutes is correct. Then, the universe continues to cool. For hundreds of thousands of years, nothing much changes in terms of structure. It is just a cooling plasma. Then, at around 380,000 years, recombination occurs. The temperature drops to about 3,000 Kelvin. Electrons can finally bind to nuclei. Neutral atoms form. The fog clears. Photons can travel freely. This is the release of the cosmic microwave background radiation. We can see this light today. It is the baby picture of the universe. It shows us the density fluctuations at that time. They are tiny, 1 part in 100,000. The universe is incredibly smooth. This smoothness is the problem. If the universe is this smooth, how do we get galaxies? Gravity must amplify these tiny fluctuations. Overdense regions attract more matter. Underdense regions lose matter. This is gravitational instability. But gravity is weak. It takes time to work. After recombination, the universe enters the dark ages. There are no stars. There is no light source other than the cooling CMB. It is a vast, dark expanse of neutral hydrogen gas. This period lasts for millions of years. Gravity is quietly working in the dark. Dark matter, which does not interact with light, begins to clump first. It forms halos. These halos provide the gravitational wells for the normal matter to fall into. The gas falls into the dark matter halos. It compresses. It heats up. Eventually, it reaches the critical density and temperature for fusion. The first stars ignite. This is cosmic dawn. This is expected to happen around 100 million to 200 million years after the Big Bang. These are the population 3 stars. They are the first sources of light. Since the CMB, they end the dark ages. Their radiation begins to ionize the surrounding hydrogen. This is the epoch of rionization. Bubbles of ionized gas form around the first stars and galaxies. These bubbles grow and merge. Eventually, the entire universe becomes ionized again. This process takes hundreds of millions of years. It finishes around 1 billion years after the Big Bang. During this time, galaxies are forming, but they are small. They are building blocks. The Standard Model predicts hierarchical merging. Small galaxies merge to form larger ones. It is a bottom-up process. You do not start with a giant. You start with dwarfs. Over billions of years, these dwarfs collide. Their stars mix, their gas mixes, their dark matter halos merge. This is how you get a Milky Way. This is how you get a massive elliptical galaxy. It is a slow, violent process. Simulations show this clearly. If you run the code with the standard parameters, you get a universe that looks like ours today. But you do not get massive galaxies at redshift 14. Let us look at the cooling time. Gas must cool to form stars. If the gas is too hot, The pressure prevents collapse. In the early universe, the gas is primordial. It is hydrogen and helium. These elements are not efficient at cooling. They do not have many spectral lines to radiate away heat. Metals are efficient coolers. They have many electron transitions that allow them to emit photons and lose energy. Without metals, gas clouds must be much more massive to collapse under their own gravity. This leads to the formation of massive stars. But it also slows down the formation rate. You cannot fragment the gas into many small stars easily. You get fewer, bigger stars. This limits the total number of stars you can form in a given time. To get 100 billion stars, you need to fragment the gas efficiently. You need metals. But metals take time to produce. This is the cooling bottleneck. The galaxy we found seems to have bypassed this bottleneck. It cooled fast. It fragmented fast. It formed stars fast. How? Perhaps the dark matter is the key. In the standard model, dark matter is cold. Cold dark matter moves slowly. It clumps on small scales first. This supports the hierarchical model. What if dark matter is warm? Warm dark matter moves faster. It washes out small-scale fluctuations. This would suppress the formation of small galaxies. It would delay structure formation even more. That makes the problem worse. What if dark matter is fuzzy? Fuzzy dark matter is a theoretical model where the particle has a very low mass, giving it a large quantum wavelength. This also suppresses small structures. What if dark matter interacts with itself? Self-interacting dark matter could transfer heat within the halo. It could change the density profile. It could make the center denser. A denser center could pull gas in faster. This could accelerate star formation. This is one of the avenues researchers are exploring. If dark matter is not cold and non-interacting, but something more complex, it could allow halos to form faster and deeper. This could explain the early massive galaxies, but it breaks other parts of the model. It affects the CMB power spectrum. It affects galaxy rotation curves. You cannot change one thing without changing everything. Let us consider the expansion rate. The age of the universe depends on the Hubble constant. If the universe is expanding faster, it is younger. If it is expanding slower, it is older. There is a tension here. The Hubble tension. Measurements of the expansion rate from the early universe, CMB, differ from measurements from the late universe, supernovae. The early universe measurement suggests a slower expansion, meaning an older universe. The late universe measurement suggests a faster expansion, meaning a younger universe. If the universe is actually older than we think, that gives more time for galaxies to form. If the age at redshift 14 is not 290 million years, but 500 million years, that doubles the available time. That helps. But it does not solve the problem completely. The discrepancy in the Hubble constant is not large enough to account for the mass of these galaxies. We would need a radical shift in the expansion history. We would need early dark energy, a component of energy that acted like dark matter in the early universe but then decayed. This would change the expansion rate at early times. It would allow structures to grow faster. It is a speculative idea, but it is gaining traction because of problems like this. The timeline is not just about time. It is about sequence. Events must happen in order. Recombination, then dark ages, then first stars, then rionization, then galaxy assembly. If we find a massive galaxy before rionization is complete, It implies that some regions were ionized very early. This creates a patchy universe. Some parts are ionized, some are not. This affects how we see the CMB. The optical depth of the CMB is a measure of how many photons were scattered by free electrons during reionization. Planck data constrains this optical depth. It suggests reionization happened later than these galaxies imply. If these galaxies existed and were bright, they should have ionized their surroundings quickly. They should have left a mark on the CMB. The fact that the CMB suggests a later reionization means either these galaxies are not as bright as we think, or they are not as numerous as we think, or the CMB interpretation is wrong. Again, we are forced to choose which pillar of cosmology to dismantle. We must also consider the concept of cosmic variance. The universe is not uniform on all scales. There are voids and there are clusters. We live in a somewhat dense region. Maybe Webb is looking at a rare overdensity, a cosmic jackpot. In this region, the density fluctuations were higher than average. Gravity worked faster. Structures formed sooner. This is possible. But Webb is looking at multiple fields. It is finding these objects in different directions. It is unlikely that every field Webb looks at is a rare overdensity. The probability decreases with each discovery. If you find one impossible object, it is an anomaly. If you find 10, it is a pattern. If you find hundreds, it is a new law. We are moving from anomaly to pattern. The architecture of time, as we drew it, is missing floors. We thought the ground floor was the Dark Ages. Then the first floor was small galaxies. Then the second floor was large galaxies. Webb has found a penthouse sitting on the ground. The structure cannot stand. This chapter serves to highlight the rigidity of the current timeline. It is not a loose suggestion. It is a calculated sequence based on fundamental physics: thermodynamics, gravity, nuclear physics. These are not easily changed. To change the timeline, you must change the physics. You must change the strength of gravity. You must change the cooling rates of atoms. You must change the nature of dark matter. You must change the expansion history. Each of these changes has ripple effects. They affect the formation of the solar system. They affect the life cycles of stars today. They affect the fate of the universe. The discovery of these early galaxies is not an isolated problem. It is a symptom of a deeper inconsistency. It suggests that the architecture of time is not as linear or as slow as we believed. Perhaps time in the early universe behaved differently. Perhaps the conditions allowed for a burst of creation that we cannot replicate in our simulations. We are looking at a universe that is more efficient, more violent, and more mature at birth than we ever imagined. And as we continue to peel back the layers, we must ask ourselves, what else is hiding in the dark? Chapter 3, The Eye of Gold. We must now turn our attention to the instrument that revealed this crisis. The James Webb Space Telescope is not merely a camera, it is a time machine. It is a marvel of engineering that required the cooperation of nations, the ingenuity of thousands of scientists, and a budget that stretched into the billions. To understand the data, we must understand the machine. Why was Webb built? It was built to see the infrared. The universe expands. Light stretches. Ultraviolet light from the first galaxies is stretched into the infrared by the time it reaches us. Hubble, the great predecessor, saw invisible and ultraviolet light. It pushed back the frontier, but it hit a wall. The wall was redshift. Beyond a certain point, the light shifts out of Hubble's range. Webb was designed to break that wall. It is equipped with a primary mirror composed of 18 hexagonal segments made of beryllium. They are coated in gold. Gold is used because it is highly reflective in the infrared spectrum. The mirror is 6.5 meters in diameter. This gives it a large, light-collecting area. It can see faint objects. But size is not the only factor. Temperature is critical. Infrared is heat. If the telescope is warm, it glows in infrared. It would blind itself. To see the faint heat of the early universe, the telescope must be cold. Webb operates at the second Lagrange point, L2, 1.5 million kilometers from Earth. Here, it can orbit the Sun in sync with the Earth. It is stable, but more importantly, it allows for the sun shield. The sun shield is the size of a tennis court. It blocks the light and heat from the Sun, Earth, and Moon. It keeps the telescope in permanent shadow. The temperature on the cold side drops to below 50 Kelvin. Some instruments go even colder, down to 7 Kelvin, using cryocoolers. This extreme cold allows the detectors to be sensitive to the faintest photons. Without this cooling, the discovery of these early galaxies would be impossible. The noise would drown the signal. The engineering required to unfold this structure in space was unprecedented. The mirror folded to fit inside the rocket. The sun shield folded like origami. Every deployment had to work perfectly. There were hundreds of single points of failure. If one failed, the mission was over. They all worked. The telescope opened its eye, and it looked. The instruments on board are specialized. NIRCam, the near-infrared camera, takes the images. It sees the light that has been stretched from the ultraviolet and visible into the near-infrared. It found the candidates. It saw the bright dots in the deep fields. But images are not enough. We need spectra. NIR-SPEC, the near-infrared spectrograph, is the workhorse for confirmation. It can observe up to 100 objects simultaneously using microshutters. These are tiny doors that open and close to let light in from specific galaxies. This multiplexing capability is crucial. The sky is full of objects. You cannot spend hours on each one individually. You need to screen them. NIR-SPEC allows scientists to take spectra of hundreds of candidates in one go. This is how the confirmation happened. This is how the red shifts were measured. The precision of NIR-SPEC is remarkable. It can detect the subtle dips in the spectrum that indicate the presence of specific elements. It can measure the velocity of the gas. It can measure the temperature. It provides the physical diagnostics needed to turn a dot of light into a physical object. Then there is MIRI, the mid-infrared instrument. It sees even longer wavelengths. This is important for dust. Dust emits in the mid-infrared. If these early galaxies have dust, MIRI should see it. MIRI also needs to be colder than the rest of the telescope. It has its own cryocooler. The data from MIRI complements NARCam and NIR-SPEC. It gives a fuller picture of the energy distribution. Together, these instruments cover a wide range of the infrared spectrum. They allow astronomers to construct the spectral energy distribution of the galaxy. From this, they derive the mass, the age, the star formation rate, and the dust content. It is a complex inversion problem. You take the light and you work backward to the source. You use models of stellar populations. You fit the data to the models. This is where the uncertainty lies. The models are based on physics we know from nearby stars. We assume the first stars behave like nearby stars, just with different metallicity. If the first stars behave differently, the models are wrong. The telescope is perfect. The data is perfect. The interpretation might be flawed, but the telescope itself has limitations. It is diffraction limited. At longer wavelengths, the resolution decreases. Webb cannot see the structure of these early galaxies in detail. They are point sources. We do not know if they are spirals, ellipticals, or irregular blobs. We do not know if they are merging. We infer the mass from the light. This inference relies on the mass-to-light ratio. If the stars are bottom-heavy, mostly small, dim stars, the mass is higher than if they are top-heavy, mostly big, bright stars. We cannot count the stars individually. We see the integrated light. This introduces systematic errors. However, the errors are not large enough to explain away the discrepancy. Even if we assume the most favorable conditions for the standard model, the galaxies are too massive. The telescope is not lying. The light is real. The energy output is real. The only variable is the source. The deployment of Webb was a moment of global anticipation. When the first images were released, the deep field showed galaxies everywhere. Thousands of them. Many were high redshift. The community was excited. But as the data was analyzed, the excitement turned to confusion. The numbers kept coming in. Redshift 10, redshift 12, redshift 14. Each step back in time should yield fewer, smaller galaxies. Instead, the abundance remained high. The masses remained high. This was not anticipated. The mission's success criteria were met. But the scientific return was disruptive. The engineers built a telescope to see the first light. They succeeded. But the first light was brighter than expected. It was too bright. It was like turning on a lamp in a room you thought was empty. The glare revealed things you wished to remain hidden. The hidden things are the inconsistencies in our understanding. Consider the data processing pipeline. The raw data from the telescope is not an image. It is a stream of digital counts. It must be calibrated. Bad pixels must be removed. Background noise must be subtracted. Cosmic rays must be flagged. This is done by sophisticated software. There is always the risk of artifacts. A cosmic ray hit could look like a bright object. A reflection could look like a galaxy. The teams are aware of this. They are skeptical. They check and recheck. They use different pipelines. They compare with other telescopes. Ground-based telescopes like ALMA, the Atacama Large Millimeter Array, follow up on these targets. ALMA sees in radio waves. It can detect the dust and the gas directly. It confirms the presence of matter. When ALMA looks at these high redshift candidates, it often finds emission lines from carbon or oxygen. This confirms the redshift. It confirms the presence of metals. It confirms the mass. The multi-wavelength approach strengthens the case. It is not just Webb seeing things. It is the collective eye of humanity seeing things. The cost of this knowledge is high. Webb was delayed for years. It went over budget. It was nearly canceled. But it launched. And now it is rewriting textbooks. The scientists who built the instruments are now the ones questioning the models they used to design the observations. It is a strange loop. We build tools based on theory. The tools test the theory. The theory fails. We must build new tools, or we must change the theory. Currently, we are changing the theory. The eye of gold has shown us that the universe is not what we thought. It is more complex. It is more surprising. It is more challenging. The technical achievement of Webb is undeniable, but its scientific legacy will be defined by the problems it created, not just the answers it gave. It has opened a Pandora's box of cosmological questions, and we are only just beginning to look inside. The sensitivity of Webb allows it to see the faint glow of the universe's infancy. But sensitivity brings noise. The background is not empty. There is zodiacal light. There is light from foreground galaxies. There is instrumental noise. Separating the signal from the noise requires statistical rigor. The teams use Bayesian inference. They calculate the probability of the data given the model. They find that the probability of the standard model given the data is low. This is the statistical definition of a crisis. When the p-value drops below a certain threshold, you reject the hypothesis. The hypothesis is lambda CDM structure formation. The data rejects it. This is not a casual observation. It is a statistical significance. The eye of gold does not blink. It stares relentlessly at the deep field, and it refuses to look away from the impossible. As we conclude this section on the telescope, we must acknowledge the human element. Behind the data are people, astronomers who spent their careers studying galaxy formation. They are now watching their life's work being challenged. Some are resistant. They look for errors. They look for alternatives. This is healthy. Science progresses through skepticism, but the weight of evidence is mounting. The telescope is robust. The data is consistent. The anomaly is persistent. The eye of gold has seen the truth, and the truth is uncomfortable. It tells us that we are strangers in our own universe. We thought we knew the history of the cosmos. We thought we could read the timeline like a book. But the book has pages missing. Or perhaps the pages are written in a language we do not yet speak. The telescope gave us the words. Now we must learn the grammar. And the grammar of the early universe seems to follow different rules than the grammar of the present day. Chapter 4: The Crisis in Cosmology. The discovery of these early massive galaxies does not exist in a vacuum. It is part of a larger pattern. It is part of a growing crisis in cosmology. For the past decade, tensions have been building. Cracks have been appearing in the facade of the Standard Model. The Hubble tension is the most famous. As mentioned earlier, the expansion rate measured from the early universe does not match the expansion rate measured from the late universe. The difference is small in percentage terms, but large in statistical significance. It is 5 sigma. In physics, 5 sigma is the threshold for discovery. It means it is not a fluke. It means the model is missing something. Then there is the S8 tension. This relates to the clumpiness of matter. The CMB predicts a certain amount of clumping. Weak lensing surveys, which measure how light bends around matter in the late universe, suggest less clumping. The universe is smoother than it should be. These tensions suggest that the physics of the early universe and the physics of the late universe are not connecting properly. The early massive galaxies add fuel to this fire. They suggest that structure formed too fast. This is related to the S8 tension. If structure formed faster, maybe the clumping is different. Maybe the growth of structure is not linear. Maybe gravity is stronger on large scales in the early universe. Or maybe dark energy was different. The standard model assumes dark energy is a cosmological constant. It is constant in time and space. It does not change. But what if it evolves? What if early dark energy existed? This would change the sound horizon at recombination. It would change the CMB peaks. It would change the inferred Hubble constant. It could resolve the Hubble tension, and it could allow for faster structure growth. It is a convenient solution. But it requires new physics. It requires a new field in the universe, a scalar field that acted like dark energy for a brief period and then vanished. We have no direct evidence for this field, but the anomalies are pointing toward it. Another aspect of the crisis is the nature of dark matter. We assume it is cold and collisionless. But we have not detected it. We have not found the particle. Direct detection experiments have come up empty. Indirect detection has come up empty. Colliders have not produced it. Maybe it is not a particle. Maybe it is a modification of gravity. MOND, Modified Newtonian Dynamics, proposes that gravity behaves differently at low accelerations. It explains galaxy rotation curves without dark matter, but it struggles with the CMB. It struggles with clusters. However, relativistic versions of MOND are being developed. They attempt to fit all the data. The early galaxies pose a challenge for MOND as well. Structure formation in MOND is faster than in lambda CDM. This could help explain the early galaxies, but MOND has its own problems. It is not a complete theory. It is a phenomenological fix. The crisis is that neither model fits perfectly. We are stuck between a dark matter we cannot find and a modified gravity we cannot confirm. The early galaxies force us to confront the possibility of systematic errors in our understanding of stellar physics. Maybe the initial mass function is not universal. The initial mass function describes the distribution of stellar masses at birth. We assume it is the same everywhere, but in the early universe, the conditions were different. No metals, high radiation density. Maybe the stars formed much more massive. Maybe they formed in bursts. Maybe the feedback mechanisms were different. If the stars are more massive, they are brighter. This reduces the mass required to explain the light. But it increases the rate of enrichment. It creates metals faster. This could explain the dust. But it creates a supernova problem. Too many supernovae would blow the gas out of the galaxy. The galaxy would stop forming stars. We do not see evidence of this shutdown. The galaxies appear to be forming stars continuously. This implies a regulation mechanism we do not understand. Perhaps the dark matter halo is so massive that it holds the gas in despite the supernovae. This returns us to the dark matter problem. The halo must be huge. Let us consider the philosophical implication. Science progresses by falsification. We propose a model. We test it. If it fails, we replace it. This is how we moved from Earth-centered to Sun-centered. This is how we moved from Newton to Einstein. We are currently in a phase of falsification. The lambda CDM model is being falsified. It is not dead yet. It is still the best model we have. It fits most of the data, but it does not fit all of the data. And the data that does not fit is becoming harder to ignore. The early galaxies are the latest. Blow. They are not the only one, but they are the most visual. They are the most tangible. You can see the picture. You can see the galaxy. It is hard to argue with a picture. The Hubble tension is abstract. It is about numbers. The early galaxies are concrete. They are objects. This makes the crisis more public. It makes it more urgent. The community is responding. New simulations are being run. They are tweaking the parameters. They are adding new physics. They are trying to reproduce the Webb results. So far, success is limited. Some simulations can produce 1 or 2 massive galaxies, but not hundreds, not consistently. The probability is too low. To match the data, you have to change the initial conditions. You have to start with a universe that is more clumpy. But the CMB says the universe is smooth. This is the conflict. The CMB says smooth. The galaxies say clumpy. Both cannot be right. One of the observations must be reinterpreted, or the physics connecting them must be changed. This is the work of the next decade. Cosmologists will be wrestling with this problem. Grants will be written. Telescopes will be built. Theories will be proposed and discarded. We must also consider the role of bias. Are we seeing what we want to see? When Webb launched, everyone expected discoveries. There is pressure to find something new. There is pressure to publish. Could this lead to confirmation bias? Possibly. But the data is public. Anyone can download it. Anyone can analyze it. Independent teams are checking the results. The consensus is growing. It is not just one team. It is the community. The bias argument is weakening as more data comes in. The reality is settling in. The universe is strange. It is not conforming to our expectations. This is the beauty of science. It humbles us. It reminds us that nature is under no obligation to make sense to us. We construct models to make sense of it. When the models fail, we must change. We must adapt. The crisis is also an opportunity. It is a chance to learn something fundamental. Every crisis in physics has led to a breakthrough. The ultraviolet catastrophe led to quantum mechanics. The precession of Mercury led to general relativity. The Michelson-Morley experiment led to special relativity. These were all moments when the data did not fit. This could be one of those moments. We could be on the verge of a new understanding of gravity, or matter, or time. The early galaxies are the hint. They are the clue. If we can solve why they exist, we might unlock the next level of physics. It is a thrilling prospect. But it is also frightening. It means everything we know is provisional. It means the textbook is not finished. It means the work is not done. For scientists who wanted a clean, finished model, this is a nightmare. For scientists who want to discover, this is a dream. As we move deeper into this investigation, we must keep the broader context in mind. This is not just about one galaxy. It is about the consistency of physical law across time and space. If the laws of physics were different in the early universe, what does that mean? It means the constants are not constant. It means the vacuum is not empty. It means the universe is dynamic in ways we did not anticipate. The fear scientists feel is the fear of the unknown. It is the fear of standing on the edge of a cliff and realizing the map ends. But beyond the cliff is new territory. It is uncharted. It is waiting to be explored. The telescope has given us the bridge. We must have the courage to cross it. The crisis in cosmology is not the end of science. It is the beginning of a new chapter. And the first sentence of that chapter was written by a galaxy that should not exist. Chapter 5: The Invisible Scaffolding. To understand why these galaxies are so terrifying to the standard model, we must look at what holds them together. We have spoken of gravity, but gravity alone is insufficient. Visible matter, the stars, And gas, we see, does not have enough mass to generate the gravitational pull required to keep a galaxy intact. If a galaxy relied only on the gravity of its stars, it would fly apart. The stars on the outer edges would escape into the void. This was discovered decades ago by Vera Rubin, who observed the rotation curves of spiral galaxies. They spun too fast. There had to be more mass than we could see. We called this dark matter. It is the invisible scaffolding of the universe. It is the skeleton upon which the flesh of stars is hung. In the Standard Model, dark matter is cold. It moves slowly. It clumps easily. It forms halos. These halos are the nurseries of galaxies. Gas falls into them. Stars form inside them. The size of the halo dictates the size of the galaxy. If we find a massive galaxy early in the universe, we must infer a massive dark matter halo. This is the crux of the issue. The Standard Model of cosmology, lambda CDM, predicts the distribution of these halos. It predicts how many small halos there should be and how many large halos there should be at any given time. This prediction comes from the initial conditions set by the cosmic microwave background. The fluctuations in the CMB are the blueprint. They tell us the density of dark matter. They tell us the speed of dark matter. They tell us how it clumps. When we run simulations based on these blueprints, we get a specific hierarchy. Small halos form first. Large halos form later through mergers. This is the bottom-up scenario. It is robust. It has worked for 30 years. It explains the large-scale structure of the universe today. The cosmic web of filaments and voids matches the simulations perfectly. But it does not match the early universe. The early massive galaxies imply that large halos formed too quickly. This suggests that the dark matter might not be cold. If dark matter is warm, it moves faster. Fast-moving particles smooth out small-scale fluctuations. They stream away from dense regions. This suppresses the formation of small halos. This is known as free streaming. Warm dark matter would result in fewer dwarf galaxies. It would delay the formation of structure. This seems counterintuitive. If warm dark matter delays structure, how does it help with early massive galaxies? It doesn't. It makes the problem worse. If anything, warm dark matter would make it harder to form large structures early. So warm dark matter is likely not the solution. Unless the definition of warm is nuanced. Unless there is a mix. But the data from the Lyman alpha forest, which measures the distribution of gas along the line of sight to quasars, constrains the temperature of dark matter. It suggests dark matter must be cold. It cannot be too warm. So we are backed into a corner. Cold dark matter predicts too few large halos early on. Warm dark matter predicts even fewer. What if dark matter interacts with itself? In the Standard Model, dark matter particles pass through each other like ghosts. They only interact via gravity. This is cold dark matter, CDM. But what if they collide? What if they scatter? This is self-interacting dark matter, SIDM. If dark matter particles collide, they can transfer energy. In the center of a halo, this can create a core rather than a cusp. It can change the density profile. A denser core could pull gas in more efficiently. It could accelerate the cooling of the gas. It could trigger star formation earlier. This is a promising avenue. SIDM could potentially explain the high density of these early galaxies. It could allow halos to collapse faster than standard CDM. But SIDM has constraints. If dark matter interacts too strongly, It would affect the shape of galaxy clusters. We observe cluster collisions like the bullet cluster. The dark matter separates from the gas. This suggests dark matter does not interact strongly. There's a narrow window where SIDM could work. It must interact enough to affect galaxy formation, but not enough to disrupt cluster dynamics. Finding this window is the work of current research. Then there is fuzzy dark matter. This is a theoretical model where the dark matter particle is extremely light. It has a large de Broglie wavelength. On galactic scales, it behaves like a wave rather than a particle. This wave nature suppresses small-scale structure. It creates a minimum mass for halos. Below this mass, halos cannot form. This solves the missing satellites problem, where simulations predict more dwarf galaxies than we observe. But again, this suppresses early structure. It makes it harder to form massive galaxies early. So fuzzy dark matter faces the same challenge as warm dark matter. It seems that most modifications to dark matter tend to suppress structure, not enhance it. To enhance structure, we need something that clumps faster. We need something that amplifies the initial fluctuations. This leads us to the possibility of early dark energy. We discussed this briefly before, but it deserves a deeper examination. Dark energy is the force driving the accelerated expansion of the universe today. It is dominant now. In the early universe, it should be negligible. But what if it wasn't? What if there was a component of dark energy that was active in the first few 100,000 years? This early dark energy, EDE, would contribute to the energy density of the universe. It would change the expansion rate. A faster expansion rate in the early universe would change the sound horizon. This is the distance sound waves could travel in the plasma before recombination. This distance is imprinted on the CMB. It is used to calculate the Hubble constant. If the sound horizon is smaller, the Hubble constant is higher. This could resolve the Hubble tension. But how does it affect structure formation? If the expansion rate is different, the growth of perturbations is different. Gravity competes with expansion. If expansion is faster, gravity has a harder time pulling matter together. This would suppress structure. So EDE typically makes the structure formation problem worse, unless the EDE decays in a specific way, unless it converts into matter. If early dark energy decays into dark matter, it could inject extra matter into the universe at a late time. This would increase the density of dark matter available for structure formation. It could boost the growth of halos. This is a complex scenario. It requires fine-tuning. The decay must happen at the right time. It must produce the right amount of matter. But it is a possibility. It links the Hubble tension to the structure formation problem. It suggests that the two crises are related. They are symptoms of the same underlying physics. We must also consider the possibility that dark matter is not a particle at all. Perhaps it is a manifestation of something else. Primordial black holes. These are black holes formed in the very early universe, not from stars, but from density fluctuations. If dark matter consists of primordial black holes, they could act as seeds for galaxy formation. Gas could accrete onto them quickly. They could grow into supermassive black holes. They could pull stars together. This could explain the early massive galaxies and the early quasars simultaneously. It is an elegant solution. But primordial black holes are constrained by microlensing surveys. We look for them passing in front of stars. We have not seen enough of them to account for all dark matter. They could be a fraction. They could be the seeds. But they cannot be the whole story. Unless they are in a mass window we haven't looked at yet. There are gaps in the constraints. There is room for them to hide. The search for dark matter particles continues underground. Detectors like Xenon T and Lux Zeppelin are waiting for a WIMP to hit a xenon atom. They are incredibly sensitive. They are shielded from cosmic rays. They are cooled to reduce noise. They have been running for years. They have found nothing. The parameter space for WIMPs is shrinking. This null result adds to the tension. If dark matter is not a WIMP, what is it? An axion? Axions are lighter. They convert to photons in magnetic fields. Experiments like ADMX are looking for them. They have not found them yet. Sterile neutrinos? They decay and emit X-rays. We look for X-ray lines from galaxies. There have been hints, like the 3.5 kiloelectron-volt line, but they are not confirmed. The lack of detection is frustrating. It forces us to look at the astrophysical data more closely. If we cannot find dark matter in the lab, we must find it in the sky. The early galaxies are a form of detection. They are telling us about the properties of dark matter through their existence. They are saying, whatever dark matter is, it allowed us to form quickly. This implies that the interaction between dark matter and baryonic matter might be more complex. In the standard model, they only interact via gravity. But what if there is a dark force? A force that acts only on dark matter. This could create dark atoms, dark molecules, dark chemistry. This dark sector could have its own physics. It could cool down. It could form structures independently of normal matter. Then, through some portal, it interacts with normal matter. This could transfer heat. It could compress gas. It could trigger star formation. This is speculative. It is beyond the standard model, but the standard model is failing. Speculation is necessary. We are in a regime where conventional wisdom is insufficient. We need radical ideas. The fear among scientists is that we are adding epicycles. In the days of Ptolemy, when the planets didn't move as predicted, astronomers added circles upon circles to fix the model. They kept the Earth at the center. They made the model complex. Eventually, Copernicus moved the sun to the center. The model became simple. Are we adding epicycles to lambda CDM? Are we adding early dark energy, self-interacting dark matter, primordial black holes, and modified initial conditions just to save the model? Or are these clues to a deeper truth? The difference between an epicycle and a discovery is only clear in hindsight. Currently, we are in the thick of it. We are adding complexity. We are trying to fit the data. The early galaxies are the new retrograde motion. They are the anomaly that refuses to go away. Consider the feedback loops. In galaxy formation, feedback is crucial. Stars explode. Black holes jet. This energy heats the gas. It stops star formation. This self-regulation keeps galaxies from growing too fast. In the early universe, this feedback must have been inefficient. Why? Maybe the gas was denser. Maybe the gravity was stronger. Maybe the feedback energy escaped easily. If feedback is weak, galaxies grow fast. This is a possible explanation. It does not require new physics. It requires better understanding of hydrodynamics. Simulations are getting better. They are including more physics, magnetic fields, cosmic rays, turbulence. Maybe the early galaxies are not a crisis of cosmology, but a crisis of astrophysics. Maybe we just didn't model the gas correctly. This is the hope of many cosmologists. They want the problem to be astrophysical. They want to keep lambda CDM intact. They want to say, we just didn't know how stars formed back then. But the mass is the problem. The mass requires dark matter. The dark matter requires cosmology. You cannot separate them. The astrophysics is tied to the cosmology. If the galaxy is massive, the halo is massive. If the halo is massive this early, the cosmology is challenged. You cannot fix it with just star formation physics. You need the halo to be there. And the halo is a cosmological object. So the crisis remains. It permeates every layer of the model. The invisible scaffolding is shaking. We built our understanding of the universe on the assumption that dark matter is cold and passive. We assumed it was a silent partner. But the early galaxies suggest it was active, it was dynamic, it was ready to build. This changes the narrative of the universe. It changes the story from a slow, gradual assembly to a rapid, violent eruption. The universe did not wake up slowly. It woke up screaming. It formed structures with urgency. This implies a higher energy density in the early stages. It implies a different thermal history. It implies that the dark sector is richer than we thought. As we probe deeper, we must ask, what is the limit? How early can a galaxy form? Webb is pushing the limit. It is finding galaxies at redshift 16, redshift 20. Where does it stop? Is there a hard limit? Theoretically, there is. You cannot form a galaxy before atoms exist. You cannot form a galaxy before dark matter clumps. There is a physical minimum time. We are approaching that minimum. If we find galaxies at redshift 30, it would be catastrophic for the Big Bang model itself. It would imply structure before recombination. That is impossible in standard physics. We are not there yet, but we are getting closer to the boundary. Every new record-breaking galaxy pushes us closer to the edge. And the edge is where the new physics lives. The invisible scaffolding is not just holding galaxies, it is holding our confidence. If it breaks, we fall. We fall into uncertainty. But uncertainty is where science lives. Certainty is dogma. Uncertainty is inquiry. The shaking of the scaffolding is a good thing. It means we are testing it. It means we are not accepting it blindly. The early galaxies are the stress test, and the structure is creaking. We need to reinforce it or rebuild it. Either way, the result will be stronger. The dark matter hypothesis is not dead, but it is wounded. It needs healing, and that healing will come from understanding these impossible objects. They are the key to the dark sector. They are the lanterns in the dark. They show us where the matter is. They show us where the gravity is. They show us where the model is broken, and they show us where to look for the fix. Chapter 6: The Gravity Alternative. If dark matter is the invisible scaffolding, gravity is the force that binds it. For a century, general relativity has been the gold standard of gravity. Einstein's theory predicts how matter curves space-time. It predicts how light bends. It predicts how orbits precess. It has passed every test, from the deflection of starlight during an eclipse to the detection of gravitational waves. It is robust, but it struggles on galactic scales. Without dark matter, general relativity cannot explain rotation curves. This is why dark matter was proposed, to save gravity. But what if gravity is the problem? What if general relativity is incomplete? This is the path of modified gravity. The most famous alternative is MOND, modified Newtonian dynamics, proposed by Mordechai Milgram in the 1980s. It suggests that at very low accelerations, gravity behaves differently. It becomes stronger. This explains rotation curves without dark matter. It fits the data of local galaxies remarkably well, better than dark matter in some cases. But MOND is non-relativistic. It is a modification of Newton, not Einstein. To fit cosmology, we need a relativistic theory. TeVe's tensor vector scalar gravity was an attempt. It failed to fit the CMB. Other theories followed. MOG, modified gravity. They tried to reproduce the success of MOND on small scales while fitting the large-scale structure. It is a difficult balance. The early massive galaxies pose a unique challenge for modified gravity. In MOND, structure formation is faster. Gravity is stronger at low accelerations. This helps. It allows galaxies to form quicker. This could explain the early massive galaxies. It is a point in favor of MOND. But MOND struggles with the CMB. The CMB peaks require dark matter to fit the data. The ratio of baryonic matter to dark matter is encoded in the peak heights. MOND has no dark matter, so it must explain the peaks differently. Some proponents suggest neutrinos, hot dark matter, but neutrinos free stream. They suppress structure. This brings us back to the structure problem. It is a tug of war. MOND solves the galaxy problem, but creates the CMB problem. Lambda, CDM solves the CMB problem, but creates the galaxy problem. This dichotomy is the heart of the crisis. We have two regimes: the early universe, CMB, and the late universe, galaxies. They do not agree. The early massive galaxies bridge these regimes. They are early objects that look like late objects. They have the mass of late galaxies, but the age of early ones. This confuses the distinction. If MOND is right, structure should form early. This fits the Webb data. But then why does the CMB look like it has dark matter? Maybe the CMB interpretation is wrong. Maybe there is a systematic error in the Planck data. This is a bold claim. Planck was incredibly precise, but precision does not guarantee accuracy. If the model used to interpret the data is wrong, the results are wrong. Consider the possibility that gravity changes over time. Maybe general relativity is only valid in certain epochs. Maybe in the early universe, gravity was stronger. This is known as varying G. The gravitational constant might not be constant. If G was larger in the past, gravity would be stronger. Structure would form faster. Galaxies would grow quicker. This could explain the early massive galaxies. But it affects nucleosynthesis. Big Bang. Nucleosynthesis depends on the expansion rate, which depends on gravity. If G was different, the abundance of elements would be different. We observe the abundance of helium and deuterium. It matches the standard model. This constrains varying G. It cannot vary too much, but maybe it varied just enough. Maybe there was a transient increase in gravity, a gravitational pulse. This is speculative, but it fits the need for faster formation. Another angle is the curvature of space. General relativity assumes a flat universe. The CMB suggests the universe is flat, but recent data suggests a closed universe, a positive curvature. If the universe is closed, the geometry is different. The volume is smaller. The distances are different. This affects the calculation of mass and age. If the universe is closed, the early galaxies might be closer than we think. they might be less massive. This could resolve the impossibility, but the evidence for a closed universe is weak. It is a slight preference in the data, not a discovery. But it is a hint. It suggests that our assumption of flatness might be an approximation. And approximations break down at the edges. The fear of modifying gravity is high. General relativity is beautiful. It is geometric. It is elegant. To change it feels like vandalism? Scientists are reluctant. They prefer to add dark matter. Dark matter is invisible. It is easy to add. You just say, there is more mass. Modifying. Gravity changes the laws of physics. It changes how planets orbit. It changes how light travels. It has consequences everywhere. Dark matter is contained. It is a substance. Gravity is a law. Changing a law is harder than adding a substance. This is why dark matter is the preferred solution. It is the path of least resistance. But if dark matter does not exist, we must change the law. The early galaxies are pushing us toward that cliff. Let us consider the equivalence principle. This is the foundation of general relativity. Inertial mass equals gravitational mass. All objects fall at the same rate. Modified gravity theories often violate this. They introduce a fifth force. This force acts differently on different materials. We test this in labs. We drop atoms. We measure the fall. So far, the equivalence principle holds. This constrains modified gravity. It must be subtle. It must only appear on large scales. This is the chameleon mechanism. The force hides in dense environments. It reveals itself in the void. This allows modified gravity to pass local tests while affecting galaxies. It is a clever trick, but it adds complexity. It feels like an epicycle. The early galaxies do not care about our preferences. They exist. They demand an explanation. If dark matter cannot explain them, and modified gravity can, we must listen. But modified gravity has its own failures. It struggles with galaxy clusters. The bullet cluster is the biggest hurdle. The mass is separated from the gas. This looks like dark matter. Modified gravity must explain this separation. It is difficult. Some theories suggest that the fifth force acts on the gas but not the stars. This is ad hoc. It is not satisfying. The community is stuck. We have two imperfect models. One fits the early universe better, lambda CDM. One fits the late galaxy dynamics better, MOND. The early massive galaxies blur the line. They are early objects with late dynamics. They support MOND's prediction of fast formation. But they exist in a universe that looks like lambda CDM's CMB. This suggests a hybrid model. Maybe there is dark matter and modified gravity. Maybe both are true. This is heresy to purists, but nature does not care about purity. Maybe dark matter exists, but interacts via a modified force. Maybe gravity is general relativity, but dark matter has complex physics. The solution might be a combination. The crisis is forcing us to break down the silos. Cosmologists and galaxy dynamicists are talking. They are comparing notes. They are realizing that the problems are connected. The Hubble tension, the S8 tension, the early galaxies. They are all symptoms. The disease is our understanding of gravity and matter. We must also consider the quantum nature of gravity. General relativity is classical. It does not include quantum mechanics. At the early universe, energies were high. Quantum effects should matter. We do not have a theory of quantum gravity. String theory, loop quantum, gravity. These are candidates. They might predict different behavior in the early universe. Maybe gravity was repulsive at some point. Maybe there was a bounce instead of a bang. These theories are hard to test. But the early galaxies are a test. They probe the high-energy regime. They probe the interface of quantum and classical. If we can model them correctly, we might get a hint of quantum gravity. The fear here is that we are not smart enough, that the math is beyond us, that the universe is too complex. But history suggests otherwise. We solved the motion of planets. We solved the atom. We solved the gene. We will solve this, but it will require humility. We must be willing to let go of Einstein if the data demands it. We must be willing to let go of dark matter if the particles are not found. The early galaxies are the judge. They are the evidence. They are silent, but their light speaks. It says, something is wrong. It says, look closer. It says, do not be afraid to change. The gravity alternative is not just about equations. It is about perspective. It is about how we view space and time. If gravity is modified, space and time are different. They are not the stage. They are the actors. They participate. They evolve. The early universe might have had a different geometry, a different topology. This affects how light travels. It affects how we measure distance. The redshift might not be purely cosmological. There might be a gravitational component. This is tired light. It was disproven long ago. But maybe it deserves a second look. Maybe the light loses energy interacting with the vacuum. This would change the distance scale. It would make the universe older. It would give more time for galaxies to form. This is a radical idea. It is unlikely. But in a crisis, all ideas must be examined. The struggle between dark matter and modified gravity is the defining battle of modern cosmology. The early massive galaxies are the new battlefield. They are the terrain where the war will be won or lost. Every new galaxy found is a soldier. Every spectrum is a weapon. The data is accumulating. The tide is turning. For decades, dark matter was the undisputed king. Now it is being challenged. The king is wearing no clothes. The early galaxies are the children pointing it out. It is an uncomfortable moment. But it is necessary. The truth is more important than comfort. The universe is not here to make us feel secure in our models. It is here to be understood, and understanding requires change. As we move forward, we must keep an open mind. We cannot favor one theory over the other based on beauty. We must favor the one that fits the data. Currently, neither fits perfectly. This means the truth is likely something else, something we haven't thought of yet, something that combines the best of both, or something entirely new. The early galaxies are the signpost. They point the way. They say, go here. They say, look here. They are the guides in the dark, and we must follow them even if they lead us off the map. Chapter 7. The Multiverse and Initial Conditions. If the physics of the universe is not what we thought, perhaps the beginning was not what we thought. We assume the Big Bang was a singular event. We assume the initial conditions were set by inflation. Inflation is the theory that the universe expanded exponentially in the first fraction of a second. It solves the horizon problem. It solves the flatness problem. It explains the seeds of structure. It is a successful theory, but it is flexible. Too flexible. There are many models of inflation: chaotic inflation, eternal inflation, hybrid inflation. They predict different things. Some predict gravitational waves, some do not. We have not detected primordial gravitational waves. The B-mode polarization of the CMB is still elusive. This leaves inflation somewhat unverified. The early massive galaxies challenge inflation. Inflation predicts a specific spectrum of fluctuations, a nearly scale invariant spectrum. This means fluctuations are the same on all scales. This leads to a hierarchical structure, small first, then large. The early massive galaxies suggest more power on large scales. They suggest the spectrum was not scale invariant, it was tilted. There were more large fluctuations than expected. This requires a specific type of inflation, a model that produces more clumping. This is possible, but it constrains the inflation models. It rules out the simple ones. It forces us to complex ones. Again, the epicycle problem. But there is a deeper implication. If the initial conditions were different, maybe they are not unique. Maybe our universe is one of many. The multiverse. In eternal inflation, bubbles of universe form. Each bubble has different physical constants, different laws, different initial conditions. In most bubbles, structure does not form. The universe expands too fast, or it collapses too soon. Life cannot exist. We live in a bubble where structure forms. This is the anthropic principle. We observe what we can observe. But if the multiverse is real, maybe there are bubbles where structure forms faster. Maybe we are in one of those. But we measure the constants here. They seem standard. The fine structure constant, the gravitational constant. They look normal. So why the early structure? Maybe the initial conditions were not random. Maybe they were selected. This touches on philosophy, but it is relevant. If the universe is fine-tuned for life, maybe it is also fine-tuned for early structure. Maybe early structure is necessary for life. Heavy elements are needed for planets. Planets are needed for life. If galaxies form early, metals are produced early. Planets form early. Life has more time to evolve. This is a long chain of reasoning, but it connects the observation to the observer. We are here to see these galaxies because the universe allowed them to form. If they hadn't formed, we wouldn't be here. This is a tautology, but it is a perspective. Consider the possibility of a cyclic universe. The Big Bang was not the beginning, it was a bounce. The universe expands, contracts, and bounces. Each cycle resets the entropy. Each cycle changes the conditions. Maybe in this cycle, the conditions were ripe for early structure. Maybe the previous cycle left imprints. Gravitational waves from the previous cycle, black holes from the previous cycle. These could act as seeds. This is conformal cyclic cosmology. It is controversial, but it offers an alternative to the singular Big Bang. It allows for history before the beginning. It allows for inheritance. The early galaxies could be the heirs of a previous universe. This is poetic. It is also testable. There should be circles in the CMB, evidence of previous collisions. Some claim to see them. Others say it is noise. The debate continues. The initial conditions are the code of the universe. If the code is different, the output is different. We are trying to reverse engineer the code from the output. The early galaxies are a line of code we didn't expect. They suggest the loop runs faster. They suggest the variables are initialized differently. Maybe the density of matter was higher. Maybe the dark energy was negative. Maybe the dimensions were different. String theory suggests extra dimensions. Maybe they were compactified differently in the early universe. This could change the strength of gravity. It could change the forces. It could allow for faster formation. Then the dimensions settled. The universe became standard. This is a phase transition. The early universe was in a different phase, like water versus ice. The galaxies formed in the water phase. Then the universe froze. This is speculative, but it fits the data. The fear of the multiverse is that it makes science impossible. If anything can happen in some bubble, then nothing is surprising. Any observation can be explained by "we live in that bubble." This is unfalsifiable. It is not science, it is metaphysics. Scientists resist it. They want a unique theory. They want one set of laws. The early galaxies push them toward the multiverse, because to explain them with standard physics requires fine-tuning. To explain them with multiverse requires no tuning, just selection. It is the easy way out. But it might be the truth. We must be careful. We must not accept the multiverse just because it solves the problem. We must find evidence. Gravitational waves, collisions with other bubbles, imprints on the CMB. We need data. The initial conditions also relate to the arrow of time. Why does time flow forward? Entropy increases. The early universe had low entropy. This is the past hypothesis. If the universe started with low entropy, structure can form. If it started with high entropy, it would be heat death. The early massive galaxies suggest the low entropy state was very structured. It was not smooth. It was clumpy. This challenges the past hypothesis. It suggests the initial state was more complex. This affects the arrow of time. It affects the evolution of the universe. It suggests that time might not be as linear as we think. We must also consider the role of the observer. In quantum mechanics, the observer affects the system. In cosmology, the observer is inside the system. This creates paradoxes. The measure problem. How do we calculate probabilities in an infinite universe? The early galaxies highlight this. How probable are they? In a finite universe, they are rare. In an infinite universe, they are inevitable. Somewhere, there is a galaxy like this. Are we looking at the rare one or the common one? Webb sees many. This suggests they are common. This suggests the probability is high. This suggests the universe is biased toward structure. The crisis of initial conditions is a crisis of origin. We do not know where we came from. We have a model. It works well, but it has cracks. The early galaxies are widening the cracks. They are showing us the foundation, and the foundation is shaky. We need a new foundation. We need a theory of the beginning that predicts these galaxies. Inflation might need to be replaced, or modified, or understood differently. Maybe inflation was not smooth. Maybe it was patchy. Maybe some regions inflated more than others. This creates inhomogeneity. This creates early structures. This is inhomogeneous inflation. It is a valid model. It fits the data, but it is complex. The multiverse and initial conditions are the frontier. They are where cosmology meets philosophy. They are where physics ends and metaphysics begins. The early galaxies are the bridge. They are physical objects, but they imply metaphysical truths. They imply things about the nature of reality. They imply that our universe is not standard. They imply that we are special, or that we are not. The interpretation depends on the model, but the observation is solid. The galaxies are there. They are massive. They are early. They are real. And they force us to ask the big questions. Where did we come from? Why are we here? Is this the only universe? These are the questions that keep scientists awake. Not the math, the meaning. The fear is that there is no answer, that the universe is random, that there is no reason for the initial conditions, that it is just a brute fact. This is unsatisfying. Humans seek reasons. We seek causes. We seek stories. The story of the Big Bang is a good story. It has a beginning, it has a middle, it has an end. The early galaxies disrupt the story. They make the beginning messy. They make the middle confusing. They make the end uncertain. But a messy story is more real. A clean story is a fairy tale. The universe is not a fairy tale. It is complex. It is chaotic. It is beautiful. The early galaxies are part of that beauty. They are the chaos that creates order. They are the exception that proves the rule, or the rule that breaks the exception. We do not know yet, but we are looking, and the looking is the point. Chapter 8, The Future of Observation. We have discussed the object, the time, the telescope, the crisis, the dark matter, the gravity, and the origin. Now we must look forward. What comes next? The James Webb Space Telescope is just the beginning. It opened the door. But it cannot walk through it alone. We need more tools. We need more eyes. The future of cosmology depends on the next generation of observatories. They are already being built. They are already being planned. They will test the theories we have discussed. They will confirm or deny the early galaxies. They will solve the crisis, or they will deepen it. The Nancy Grace Roman Space Telescope is launching soon. It is a wide-field infrared telescope. Webb is deep. Roman is wide. Webb looks at a small patch of sky. Roman will look at huge areas. It will find thousands of early galaxies. It will map the large-scale structure. It will measure the Hubble constant. It will test dark energy. It will provide the statistical power we need. Webb found hundreds of galaxies. Roman will find millions. This will tell us if the early galaxies are rare or common. If they are common, the model must change. If they are rare, maybe we got lucky. Roman will tell us. It will reduce the cosmic variance. It will give us the big picture. Then there is Euclid, a European mission. It is already in space. It is mapping the dark universe. It is measuring weak lensing. It is measuring galaxy clustering. It will constrain the growth of structure. It will test the S8 tension. It will work with Webb. Webb finds the galaxies. Euclid measures the mass. Together, they will build a 3D map of the universe. Back to the beginning. This map will reveal the cosmic web. It will show the filaments. It will show the voids. It will show where the early galaxies sit. Are they in clusters? Are they isolated? This environment data is crucial. It tells us about the formation, history. On the ground, the extremely large telescopes, ELT, are being built. In Chile, in Hawaii, in the Canary Islands. These are giant mirrors, 30 meters, 40 meters. They will have adaptive optics. They will see as clearly as space telescopes. They will do spectroscopy. They will confirm the red shifts. They will measure the chemistry. They will see the rotation of the early galaxies. Webb cannot see rotation well. It is too small. ELT can. If we can measure the rotation, we can measure the mass dynamically. We will not rely on light. We will rely on motion. This is a direct measurement. It will settle the mass debate. If the mass is confirmed, the crisis is real. If the mass is lower, the crisis fades. ELT is the judge. We also need to look in different wavelengths, radio waves. ALMA is already doing this, but we need more. The next generation Very Large Array, NGVLA. It will see the cold gas. It will see the dust. It will see the black holes. It will penetrate the dust. that obscures the light. It will see the engines of the early galaxies. It will tell us if they are stars or black holes. This is critical. If they are black holes, the physics is different. If they are stars, the physics is different. NGVLA will distinguish. It will add another dimension to the data. Gravitational waves are the future. LISA, the Laser Interferometer Space Antenna. It will launch in the 2030s. It will detect low-frequency gravitational waves. It will detect merging black holes in the early universe. It will detect the background hum of the cosmos. This hum contains information about the early universe. It is independent of light. It is not affected by dust. It is not affected by redshift in the same way. It is a direct probe of gravity. If the early galaxies have massive black holes, LISA will hear them. It will confirm their existence. It will measure their mass. It will be the ultimate confirmation. The path forward is multi-messenger: light, gravity, neutrinos, cosmic rays. We need to combine them. We need to build a complete picture. The early galaxies are not just optical objects. They are multi-wavelength sources. They are gravitational sources. They are chemical factories. We need to study them from all angles. This requires cooperation, international cooperation, big science. The problems are too big for one country. They are too big for one telescope. They require a global effort. The crisis is uniting the community. They are sharing data. They are sharing tools. They are working together. This is the silver lining. The fear is driving collaboration. The data will come. It will be overwhelming. Petabytes, exabytes. We need new ways to analyze it. Machine learning, artificial intelligence. We need algorithms to find the patterns. The human brain cannot process it all. We need AI to help us see. This is the next step. Digital astronomy, virtual observatories. The sky is digital. We mine it. We extract knowledge. The early galaxies are the gold. We need to dig. The future is bright. Despite the crisis. The crisis means there is work to do. It means there are discoveries to be made. It means careers will be built. It means textbooks will be written. It means the next generation of scientists will have a purpose. They will solve this. They will fix the model. Or they will break it. Either way, they will advance. The future of observation is not just about better telescopes. It is about better questions. We are learning to ask the right questions. The early galaxies taught us that. They taught us to doubt. They taught us to look. They taught us that the universe is full of surprises. We must also prepare for the unexpected. The next telescope might find something else, something even stranger. Maybe life, maybe signals, maybe physics we cannot imagine. We must be ready. We must keep our minds open. We must not be dogmatic. The history of science is the history of the unexpected. The early galaxies are just the latest. Example, they will not be the last. There is always more. The universe is infinite. Our knowledge is finite. The gap is where the future lies. The investment in science is an investment in the future. These telescopes cost billions. Some say it is too much. Some say spend it on Earth. But knowledge is power. Understanding the universe helps us understand ourselves. It drives technology. It drives innovation. It inspires. The images from Webb are seen by millions. They spark curiosity. They create scientists. The value is not just in the data. It is in the inspiration. The early galaxies are inspiring. They are mysterious. They are beautiful. They draw us in. They make us want to know. This is the human spirit. It is the drive to explore. It is the reason we build telescopes. It is the reason we look up. The future of observation is the future of humanity. As we expand our reach into the cosmos, we expand our reach into ourselves. We learn our place. We learn our limits. We learn our potential. The early galaxies show us that the universe is capable of great things. It can build massive structures in the blink of an eye. It can create light in the dark. It can defy expectations. We are part of that universe. We are made of the same stuff. We are capable of defying expectations too. We are capable of solving the crisis. We are capable of understanding. The telescopes are our tools. The data is our map. The future is our destination. And we are on our way. Conclusion: we began with a silence. The silence of physicists realizing their model was broken. We end with a sound. The sound of discovery. The sound of the universe speaking. The galaxy with the mass of 100 billion stars, sitting just 290 million years after the Big Bang, is not just an object. It is a message. It tells us that we do not know everything. It tells us that our models are approximations. It tells us that reality is richer than our equations. This is not a failure. It is a success. It means science is working. It means we are learning. The fear scientists feel is not the fear of death. It is the fear of being wrong. It is the fear of the unknown. But this fear is necessary. It is the engine of progress. Without fear, we become complacent. We stop looking. We stop questioning. The early galaxies woke us up. They shook us out of our complacency. They reminded us that the universe is wild. It is not tame. It does not follow our rules. It follows its own. And our job is to listen. We have traveled through the architecture of time. We have looked through the eye of gold. We have examined the invisible scaffolding. We have questioned gravity. We have peered into the multiverse. We have looked to the future. And through it all, the galaxy remains. It sits in the deep field. It shines. It waits. It waits for us to understand. It waits for us to catch up. It is patient. It has been there for 13 billion years. It can wait a little longer. But we are hurrying. The telescopes are ready. The minds are ready. The work is beginning. What they were afraid of was not a monster. It was the truth. The truth that our understanding is incomplete. The truth that the universe is stranger than we imagined. This truth is not dangerous. It is liberating. It frees us from dogma. It frees us to explore. It opens the door to new physics, to new discoveries, to new wonders. The crisis is an opportunity. It is a gift, and we must accept it. So when you look up at the night sky, remember these galaxies. They are there. They are ancient. They are impossible. And they are real. They are the beacons of the early universe. They guide us. They show us the way. They tell us that there is more to see, more to know, more to understand. The story of the universe is not finished. We are writing it now. With every observation, with every theory, with every question, the pen is in our hands. The page is open, and the first sentence was written by a galaxy that should not exist. The silence is broken, the fear is gone, replaced by awe, replaced by curiosity, replaced by the drive to know. This is the legacy of the James Webb Space Telescope. Not just the images, but the questions. The questions are the gift. And the early massive galaxies are the biggest question of all. Why are you there? How did you form? What does it mean? We will spend decades answering. And when we do, we will be different. We will know more. We will see more. We will be closer to the truth. The universe is not afraid of us. It is waiting for us. It is inviting us. Come and see. Come and learn. Come and understand. The galaxy is waiting. The light is arriving. The story is unfolding, and we are here to witness it. This is science. This is discovery. This is what we were made for, to look into the dark and find the light, even if that light tells us we were wrong, especially if that light tells us we were wrong, because being wrong is the first step to being right, and the early galaxies are the step. They are the path. They are the way. Scientists just found what they were afraid of, and it is beautiful.